Let's try to solve the following differential equation. X cubed times the third derivative of y plus xy prime minus y equals 0. Now this equation is a Cauchy-Euler equation. How do I know? Well, because I can see that first of all it's a linear equation, and then second, I see that each term contains x raised to the power that matches the order of the derivative. So here I have third derivative and then power is 3. Here I have the first derivative and power is 1. Here I don't have a derivative, so power of x is 0, and that's why I don't see x at all. How do we solve the third order Cauchy-Euler equation? We can approach it exactly the same way as we learn how to solve second order Cauchy-Euler equations. That's by trying a solution of the form y equals x to the power m. So here it is. And of course, our goal will be to find what the power of m has to be and eventually obtain a general solution to this equation. But yeah, let's start from here. Okay, so if we assume that this might be a solution to our equation with m being a certain power, then it should satisfy our equation. Let's plug that into the equation. And to do that, I need to find the first derivative and the third derivative. So let's write that. So the first derivative will be the following. M goes to the front. I'm using the power rule. And then it's x to the power 1 less, so m minus 1. So that's the first derivative. Now to obtain third derivative, of course, I have to find the second derivative first. So it's m times, and then this power goes in the front, m minus 1 times x to the power 1 less than that, so it's m minus 2. That's the second derivative. And now the third derivative is this power goes to the front, so I have m times m minus 1, these are constants, and times m minus 2 now, and then this power gets reduced by 1, it becomes m minus 3. Okay, so y prime and, oh, that's the third derivative. And that expression will have to be plugged into the equation. Let's see what we're going to obtain. X cubed times m minus 1 times m minus 2 times x to the power m minus 3. That's that term. Plus x times the first derivative right here times m times x to the power m minus 1, that, and then minus y. Okay, so that's our y, minus x to the power m equals 0. So what I'll do next, I will simplify a couple things here. So I can see that x cubed and x to the power m minus 3 can be combined since bases are the same, and to combine them I'll have to add their powers. If I combine the powers, it's going to be 3 plus m minus 3, which will be just m. So in other words, x will be just to the power m, and then I have the rest from that term. Okay, so we combine that. And then we, using same idea, we can combine x and then x to the power m minus 1. As we add the powers, which is 1 plus m minus 1, we will also be left with just m. So then I'll have m times x to the power m. And then minus x to the power m, that's the last term. Okay, now I can see that x to the power m is the common factor. I can factor it out. And I'll have m times m minus 1 times m minus 2 plus m minus 1. That's the second factor. Now the way I look at it is this solution that I assumed, y equals x to the power m, is going to be the solution to the given differential equation with such powers or with such values of m that satisfy this equation. Now, talking about this first factor, I know that x itself cannot be equal to 0, right? X cannot be equal to 0 because if it is 0, then my differential equation disappears, right? Then those two terms disappear and I no longer have differential equation. So x is never 0, and since x is never 0, it means that this first factor cannot ever be equal to 0, right? No matter what power m I use, this is never 0. However, the second factor can be equal to 0 for certain values of m, and that's what I need to find. So what I'll do, I'll set the second factor equal to 0. And I'll need to solve this equation. Once I solve this equation, I will obtain values of m that will allow me to find solution to my differential equation. Let's think how we solve this. I'm going to simplify this expression so that I can see what kind of equation I'm dealing with. What I'll do, I'll first multiply out m minus 2, m minus 1. So by looking at this equation and checking all the terms and seeing some kind of patterns here, I should be able to use factoring method to solve this polynomial equation. So on the left-hand side, we'll have to apply the grouping method. And with the grouping method, you might have to move terms around and try different combinations. And I already did, and some of them didn't work. But what I found that works is if I put or group m cubed and -1, and then -3m squared plus 3m I'll put together. Now for the second group, so that's my first group, that's my second group. For the second group, I can see that the GCF is, well, I'll use the GCF negative 3m. Now the second group, let me just leave it alone for a second. So my second group is, I'm factoring out 3m minus 3m. I'm pulling that out, and then what I have left? I'll have m from the first term, and here I have to put -1 to obtain the second term, right? So I'll check. If I distribute -3m, I should go back to this expression. How about the first group? Now in the first group, there is no GCF, right? I can't factor anything out, well, except 1, which will not really help. However, I'm recognizing a formula here, or I'm recognizing a pattern. And what I'm looking at is the difference of 2 cubes. So what I have is m cubed minus, well, I can treat it as 1 cubed. And when we have difference of 2 cubes, then that can be factored using a formula or pattern. So let me remind you how it works. A cubed minus b cubed, so something cubed minus something else cubed, equals. And we factor it this way. A minus b times a squared plus ab plus b squared. So that's the way to factor the difference of 2 cubes. And let's follow this pattern. So it means that m cubed minus 1, I will not expand that factor the following way. First, it's going to be my binomial, where I put those two without cubes. So it's just m minus 1, and I keep same sign. And then I'll have to put here trinomial. It's, by the way, it's irreducible quadratic trinomial, so I won't be able to factor it any further. So it's square of the first one, m squared, plus their product, plus, well, 1 times m is just m, and then plus the square of the second one. Square of the second one is 1 squared is just 1, so plus 1. And by applying the formula here, now I can see that I should be able to finish this grouping method. I notice that m minus 1 is the common factor. I'm going to factor it out. m1 minus 1 I'm factoring out, and I'm writing everything else that's left. From the first term, I have m squared plus m plus 1 left, and then from the second term, I have minus 3 left, minus 3m left, like that. So it's m minus 1 times m squared minus 2m plus 1 equals 0. And now I should be able to, well, right here, now I should be able to solve this by setting each factor equals 0. So m minus 1, I set equals 0, I get m equals 1. That's the first value of m. And let me pull this up. And then the second factor is m squared minus 2m plus 1 equals 0. Now that is, so it's a quadratic equation, right? We have options here how to solve that, but the quickest ones are either factoring, or you might recognize that this is the perfect square trinomial and you can take that route. Well, if we just use basic factoring, then I'll use values -1 and -1, because -1 times -1 is +1, -1 plus -1 is -2. Okay, that works, equals 0. So m equals 1, m equals 1 from each, right? So what does this mean? So there are a couple notes or things to consider when you solve third order Cauchy-Euler differential equation. If you repeat this process, then real quick, I'm gonna, remind you what the process was. So starting from here, right? You remember all those steps as we plugged in y equals x to the power m and its derivatives into equation. You will obtain a third degree characteristic equation. So this equation that we had to solve, that is a characteristic equation. And characteristic equation, well, I should say degree of the characteristic equation should match the order of the differential equation. So if you're solving third order Cauchy-Euler differential equation, then your characteristic equation will be third degree polynomial equation. And that means that at the end, you're going to obtain 3 solutions. Now, there are different combinations of what those solutions could be. We got the case when they're all repeated, right? But there are still 3 of them. You can have 2 complex solutions and 1 real solution, or you can obtain 3 distinct real solutions. They're going to be all different. And based on that, general solution to the differential equation will have different form. But what you want to keep in mind that the general solution will have 3 terms. So it's going to be C1 times something plus C2 times something and then plus C3 times something. Now that something will be determined by the type of the solution that you use, whether it's real solution or complex solution, and whether it's repeated or distinct. Now in our case, how we form this general solution. We start by writing C1 times x to the power 1. Well, that's the only value of m we have here, x to the power 1. Now, C2, that kind of corresponds to the second value, which is the same. Well, since it's the same, well, we still have to write x to the power 1, but we don't want those two to be the same. So we will be multiplying by ln of x. And now to obtain the last term, we'll still have to put x, C3 times x to the power 1. It kind of corresponds to this third value of m, which is, again, the same. And think this way, you don't want that term to be repeating any preceding terms. So what we'll do, we kind of like take the preceding term and we'll multiply it by another ln of x. So it's going to be ln of x to the power 2. And if I had more than 3 repeated solutions, I would continue in that matter. But let me just write it out nicely. C1x, and then power 1 means that it's just x. C1x plus C2x ln of x plus C3x ln of x squared. So that's going to be the general solution to our equation.